Assalamu alaikum. Welcome to data mining, lecture 5 of data mining. Today, we will continue with our discussion on data preprocessing. So data preprocessing, as we discussed last time, involve a number of steps and techniques uh, which can be performed for any particular data mining project. So we will be discussing many of these techniques very briefly. Uh, the idea is that to give you an idea of the options that are available and their pros and cons, so that you as a data miner can then decide which one to apply and which one not to apply. So this is actually chapter 3 in the book by Han. So, and I think also chapter 2 in the other book by um, I think Tan, the Introduction to Data Mining book. So we will start with that today, and I think we won't be able to finish this. We will probably have to take it to the next lecture. Are there any questions specifically before we get started? All right. So any questions?
Yes, sir, I have one.
Yes.
Sir, in last lecture, you were talking about replacing the missing values. What if I replace all the missing values with some random numbers? Uh, will that be a problem? Instead of just going with the mean value?
The whole idea of replacing the missing value is to replace it with something that would make sense, meaning that replace it with a value that is the most probable or is the expected value for that particular entity. So if you replace it with random, then that by definition is not going to be the most probable or uh, the most likely value. So I probably not recommend replacing values with random values unless you are in a kind of fix and you want to run an algorithm that doesn't work without having missing values filled in, and you just want to fill in with something that would make the algorithm work.
Okay.
So can you think of any scenario where a random value filled in would make sense?
Mm, I don't think so. Sir, I was thinking like in the example of age, if we are giving mean age like 123.5, instead of that, we make an interval, and let's say we'll be giving random value between 20 to 25, any value.
Yes, that I think you can do that. So let's say you define an interval that is based on your expectation that the value should lie within this range, and then within that range you can pick one value randomly. So that is possible.
But
Yes.
yeah, that won't create many problems, right?
Yes, as long as the range is meaningful. I mean, the whole idea is we want to fill in values that are actually close to the true value. We don't just want to fill in any value.
Okay,
So you can
thank you.
say that to just create a bit of noise, you can create a narrow interval of age. Let's say you know that the age of, let's say, freshmen would range between, let's say, 17 and 20. So instead of taking the mean of freshmen, you can give this range and then let the algorithm pick one value from this randomly. So uniform random value from this interval. But that interval is first decided based on some knowledge of the appropriate uh, age. So for example, if you take a random number between 0 and 100 and generate a number from there, then that would not make sense if it puts in a value of 99 for a student.
Yes. Okay, thank you, sir. I got it.
All right. Any other question? So just as a refresher, so these are the major categories within which we can apply task in data preprocessing. So we have data cleaning, for example, we have data integration, we have data reduction, and data discretization. So the techniques within, there could be various techniques within each of these categories. And we are briefly discussing some of those techniques. We'll be discussing some of those techniques in this course. So last time we talked about data cleaning and we talked about some simple ways of replacing missing values or filling in missing values. And today we'll talk about, start with noise. So noise, as the name suggests, is usually random values within our recorded values, and usually it's kind of difficult to find noise or to determine whether noise exists in our data or not, unless you know more about your data generating process. But let's say if you do find out that there is noise in your data, then you can use some very simple techniques to smooth out the noise or remove the noise. So these simple techniques, for example, you can use binning. Binning is a very simple approach. So binning can be done using equi-width binning or equi-depth binning. So binning essentially is like creating a histogram, dividing your data set into equal width bins. And when I say equal width, these are widths with respect to the values of your attribute. So for example, if your attributes age and your values range between, let's say, 15 and 70, so 15 and 70 is the interval of values for this particular attribute. So the difference between the min and max is, of course, 70 minus 15, which would give you a value of 55. So if you now want to create 10 bins, and those are equi-width, you'll divide this 55 with 10 and get a bin width of 5.5. So in essence, then you will have the first bin from 15 to 20.5, and then from 20.5 to 26, and 26 to 31.5, and so on. So within each bin, you then find the values that are actually present in your data set, and then you can smooth them using one of these approaches, using smoothing by the bin mean or the median or the mode. So for example, all right. Okay. So let's say, as I said, so let's say your bin, first bin is 15 to 20.5. So let's say in your data set, you have values like within this bin, you have values like 17, maybe you have 15 as well. So you have 17 and you have 20. So let's say you have three values that fall within this interval in your data set. So instead of keeping these values, original value, you fill or replace these values with their means. You take the mean of these three, 10, 20. So 15, 17, 20, the mean for that, actually cannot do it off the head. Let me see if I can calculate it. 15 plus 17, 20 divided by 3. Calculate नहीं किया सर. Oh. So 17.3. So this is the mean for these three values. So instead of keeping the original value, you replace all these values with the mean. So the new values would be 17.33, 17.33, and 17.33. So this is essentially a smoothing. Of course, you are transforming your data, and any transformation is biased if it is deviating from the true value. So, but the idea is that you are assuming that there is noise in the data, and you found or you feel that this approach is the best way to remove this noise. So this was equi-width. Equi-bin is similar. In equi-bin, basically you decide the number of bins. Sorry, this is equi-width, and in equi-depth, so you decide the maximum number of values that may fall in each bin. So let's say if you decide that each bin should have a depth of 4, then you starting from one end of your data set, one point in the data set, let's say our data set was 15, 17, and then we have 20, and then let's say there was a 21 as well. So this would fall in the bin 1. For 4, you take 4 values from your data, put it in bin 1. Then you take the next 4, let's say 22, 23, 23, 24. So this is bin 2, and so on. And then again, after you have these values, take the mean of each bin and replace each value with the mean. So it's a kind of smoothing technique which would have some boundary effects whenever you move from one bin to the next bin. So if you have a time series data, you can use the moving average approach. So we will discuss time series later on in this course. So we will discuss that formula as well, which is also very similar. Of course, it is based on a prediction, mean prediction for the next value. So this is one way of smoothing data, which is not really a time series.
Sir, how do we decide if there is noise in the data?
Yeah, that's a good question, and it's not very easy. Generally, by definition, noise is randomness in the data, random values in the data. Unless you know you have a model for the data, meaning that you have some way of modeling your data in a mathematical way, and then you compare that model with the actual values, then you will be able to decide whether there is noise or not. So usually for many data mining tasks, we do some simple analysis. Of course, I'm not talking about the signal processing stuff. In signal processing, you do have some more sophisticated techniques, and most of those techniques do come from the idea of modeling. मॉडलिंग का मतलब ये है कि लेट्स से आपको पहले ही पता है कि ये लीनियर होना चाहिए या पैराबोलिक होना चाहिए या कोई और फॉर्मुलिक फॉर्म होना चाहिए, एंड देन यू फिट दैट मॉडल and see how it deviates from that. And if you already know that, then you can use that model to smooth the data. So that's another way of smoothing data. But the point is, if you don't know the model, and which is the case for many data mining applications, then you are just left with, you can say, educated guesses. You let the data miner look at the data, make some visualizations, find where, use some simple metrics to find outliers. Remember, we talked about various techniques, IQR, for example, look at the distribution, look at how far a value is from the IQR. So that would tell you whether there are outliers or not. So things like that would help you determine whether there is noise in the data or not. So, but there is no hard and fast way of saying, okay, this is the one approach by which you can find whether there is noise in the data or not.
Okay, sir.
So you need to get used to your data, relate that data to the business domain or the data generating process, and then make an educated guess. And then, of course, you also made to make a decision whether filling in the noise is better than leaving it like that. So that's also a difficult decision. So you might want to just leave the data as it is rather than changing it using some technique of smoothing the data.
So does usually it is left like the noise? We don't do anything with it and leave the noise.
Yes. So if you are comfortable that the noise is not massive and you're also uh, confident that you don't, or you know that you don't have any well defined way of smoothing the noise, then just leave it as it is. Don't worry about smoothing it. Of course, if your data set is ordinal, you might want to smooth by, uh, sorry, if it is nominal, you can smooth by bin mode. Uh, and you can also smooth by bin boundaries, meaning that instead of just using one value for the entire set of values within a bin, you can define some boundaries, some two values, 5% at the end, 5% at this end, middle point. For the middle, you can use the mean. For the boundaries, you can use the mean of the boundaries, and so on. So you can use some tricks like that. But again, there is no, let's say, scientific way of saying that this is better than the other. So the next technique mentioned here is regression, and this is moving toward modeling the data. So the idea is that you have some idea of the model, like a straight line or a parabola or some parametric form. So if you know that, then you fit that parametric form and use those values as the new values rather than the actual value in your data set. Similarly, you can cluster the data. So clustering is the technique for grouping data. So if you are able to group data in multiple ways, and you might find that there are some groups that are small, some groups that are big. So the small groups you can use the average within those groups. For bigger groups, you might want to divide them into smaller groups and take the average within them, and so on, for smoothing purposes. And of course, you can apply the technique of outlier detection. Outliers can also be considered as noise uh, if they are, of course, random. So, and there are techniques for outlier detection. Some very simple ways could be simple. So you can look at, for example, so for example, if something is like 3 into standard deviation away from mean. So you can consider such objects, any object that's more than 3 standard deviations away from the mean, as an outlier. Similarly, you can, there's another heuristic, you can say 3 times IQR. So IQR is what? The interval at the between the Q1 and Q3. So if 3 times IQR uh, from the mean, or sometimes from the boundaries, depends, of Q3 and Q1, if there are objects beyond that, you can consider those to be outliers. So just to give you an example, let's say IQR for age is, let's say, 20, let's say. So it means that, and of course, let's say Q1 is, let's say, 15, Q3 is, let's say, 35, then IQR would be 20. So 3 times IQR would be what? 45, right? So, and let's say the Q2 median is, let's say, 15 and 35, let's say 25. Okay. So if a value is more than or less than, uh, for example, more than 25 plus 45. So this is what 25 plus 45, 60, 70. So if you have a value greater than 70, you can consider it to be an outlier. Similarly, on the other side, 25 um, IQR is what, 20? IQR is 20. Okay, so 25 minus, sorry, IQR is 20. Mean is 25 minus 20. You get a value of 5. So if there are any value less than 5, you can consider that to be an outlier. So outliers give you an idea of noise in the data as well. And you can simply remove the outliers because it may not be useful in your analysis. So there is no smoothing that is required. You simply remove them. And of course, for smoothing and for detecting noise, you need to do a lot of visualization. So humans look at graphs of your data and decide whether there is noise, and also then decide which values to smooth, which values not to smooth, which values to discard, and so on. So a lot of, you can say, dirty work is involved here. All right, so let's move on. So move on to this slide. In general, data pre-processing is a very time-consuming and often quite costly endeavor in most real-world projects. Uh, it is estimated based on a survey that up to 70–80% of the time for any data mining project goes into data pre-processing. And the reason behind this is there are a lot of small things that you have to do, and there are a lot of things for which humans have to get involved and make decisions. So that makes things complicated and also error prone. So sometimes you make a decision, do something, and then you later on find out that it's not right. You go back and change and do it again and so on. So it's quite time consuming and as such also very costly. So let's move on to the next category of data pre-processing techniques. By the way, these categories are not like you can say fixed in stone. They're just a way of grouping some techniques. Uh, you will find that some of the techniques in these various techniques, these various categories overlap. So for example, binning can be used for data cleaning. Binning can be used for discretization. Okay, can you guys hear me, by the way? Just wondering because it looks like connection का
Yes, sir.
issue. आ रही आवाज? अच्छा, ठीक है. Mhm. All right. Okay. So we were talking about integration. Okay. So integration, as the name suggests, is you have data from multiple sources and you want to bring them together into a cohesive whole. Uh, Oftentimes, when you talk about data integration, we can think of data warehousing, for example, or creating data lakes. So, which is bringing data from multiple sources and make a big consolidated repository of data. So previously we used the word data warehousing quite commonly. Nowadays it's more popular to call them data lakes. Basically lakes का इसलिए use करते हैं because usually data is coming in continuously. So a lake is like a huge repository and you have streams coming in. So So what are the challenges that might arise in data integration? So let's look at them. So one of the challenge is the issue of redundancy. And first of all, going into redundancy, usually we have two problems. We have entity identification problem, and the second is feature slash attribute identification problem. So what are these? So what is entity? Entity is like the object that you are analyzing, maybe is a student. So maybe you have, or let's talk about a retail store. So maybe it's a customer. So maybe the customer, the same customer might be captured in the marketing database as well as in the sales database. But in both of those databases, there might be slight differences, or let's say even if there are no differences, but how would a computer know that they are the same entity? So maybe in the marketing database, you have a person called, let's say Zia, right? And Zia, let's say F. And in the sales database, you have a person called Zia, let's say Fareed. And there might be some other information saved in the, let's say, addresses, let's say DHA, address here is also DHA, and so on. So the first question to ask is, are these two the same entity? Is this the same entity or they are different? If they are the same, then of course you run into the problem of redundancy. But before you can even say whether there's redundancy, you need to determine whether they're actually the same or not. So again, this is not a trivial problem. It's not very easy. So usually in data preprocessing, we use some simple data scrubbing, I should say scrubbing, data metrics, measures to verify or to filter out possible entities that might be similar. So one way is maybe you can define some similarity measure. And we will discuss similarity measures in more detail later on. So in other words, so from the sales, for every entity in the marketing data set and for every entity in the sales data set, you compute a similarity measure. If the similarity is very high, then those two entities are likely to be same. So again, it's not fully automatic. Maybe this measure would filter out some candidates for duplicates, and then the human would finally decide whether they're duplicate or not. So again, this is kind of a dirty work. You have to go through each entity in the marketing database and compare it with every entity in the sales database, right? And then filter out the ones that are very similar. The other issue that I mentioned was attribute identification problem. What does this mean? For example, let's say in the sales database, uh, the attribute name is, let's say, for a particular, let's say name ही ले लेते name. In one database is mentioned as name, in the other database is given as NM. So how do we know that name is actually same as NM? So one way is to find out whether both entity actually are the same semantically is to look at the metadata if it exists. What is a metadata? It's like a dictionary, data dictionary. So where you describe each attribute in more detail, maybe provide a brief description, we provide uh, a domain for each attribute, maybe you provide possible, uh, you provide exceptions and possible values that are not allowed and possible values that are allowed. So some kind of a database that describes in more detail each attribute in your data set. So that's called a uh, m- da- metadata or the data dictionary. So you might want to look into that. Uh, and again, this is dirty work. Humans have to do it, but I think there are some tools available out there. They don't do a 100% good job, but there are some tools available that will be able to filter out potential issues for you. And then as human, you have to make the final decision. So one way is, as I said, look at the metadata and compare the metadata. Are these two entities exactly the same or not? These two attributes, sorry. Another way is actually you somehow compare the values of the attribute. So, so let's say you don't have the data dictionary. And so you compare the values that are given in those two dictionaries. Let's say in the name attribute, you have values like ZIA, ASIM, Wajiha, and so on. And for NM, you have values like 10, 20, 15, 30. So obviously there is no overlap in the values. One are nominal, character based, the other are numeric. So in this case, you know right away that there isn't any relationship between these two values, right? But in general, if you have two attributes, if you want to find a relationship between them, you will have to, and you have to, if you want to do it in a more systematic way and a quantitative way, you will have to compute some, you can say, correlation measure between them. So if the correlation is high, then they might be candidates for duplication. And one example, for example, could be, uh, let's say you have a data for property. Uh, in one database, you have property size represented with two attributes, length and width, the plot length and plot width. And with the other database, you just have the area. Plot length and width is not given. But if you compute the correlation between length and area, you will find a strong correlation. If you compute the correlation between width and area, there will be a strong correlation. So in this case, these attributes can be considered the same or redundant, and you might consider keeping either area or both length and width, because both length and width are required to compute the area. Of course, again, this is assuming that plot sizes are always rectangular in shape. So coming back to the correlation measures, so I'll just briefly mention some correlation measures. So first of all, so let's say we are talking about two attributes, attribute A and attribute B. Okay. So what are the options here? So let's say attribute A is nominal, attribute B is also nominal. So that's one way. Then we can have what is called nominal, nominal, and the other, let's say, is I will just use numeric here. Numeric can be ratio scaled or interval scaled. And nominal here, I can use categorical as well. So let me change it categorical. Although nominal is a much better definition, but just to make it simpler. And then, of course, there could be flip as well, but we will not consider the flip. We'll see how those are handled. And then finally, you have numeric and numeric. So these are the three possible cases, general cases, in which A is one type and B is another type. So we would like to define some ways of computing the uh, relationship between these two attributes values. So for categorical, the most common measure is the chi-square. So chi-square can be computed between these two attributes. If the chi-square is large, chi-square, by the way, varies between 0 and infinity in general. So if the chi-square is large, then it means that those two values are dependent, meaning that there's a lot of relationship between them. All right. uh, I I can go over the calculation of chi-square as well, but just hold on a little bit. So basically, this is chi-square. You can also use other measures for categorical, comma categorical. For example, you can use information gain, which is also similar to entropy. So you must have heard these names before elsewhere. Uh, so entropy can also be used to characterize the homogeneity of those two, uh, the values of those two attributes. All right. All right. So that was for categorical or nominal, for example. If you have numeric, I think all of you are familiar with this. You can compute the covariance, for example, between those two values. So if the covariance is close to 0, then it means that they're kind of independent and they have no relation. If the covariance is high, then it means that they have a linear relationship, or they are very uh, they they relate in a linear fashion to each other. So covariance can be computed to determine the relationship between two numeric attributes. Of course, if you have numeric attributes, you can also do a scatter plot. And of course, we are talking about two attributes. Scatter plots are possible for two attributes. You have one attribute's value, the other attribute's value, they become a point on a 2D surface. All those points can then be plotted and you can get an idea of the relationship between them. So if there is a well-defined relationship, whatever it may be, if as one value increases, the other value increases, so it means that they are well, very strongly related. So this is a visual way of determining the relationship between them. So covariance, of course, is a normalized form. If you use the unnormalized form, which is called the correlation, for example, the Pearson correlation coefficient, for example. So now, what about if you have one is, let's say, numeric or ordinal, and the other is nominal or categorical? So let's say categorical, let's say numeric and categorical. So how can you use this? So in this case, you have a number of measures. So in this case also you can use information gain / entropy. So one is, for example, I can give you an example, like let's say you have gender and let's say income, for example. So one is numeric, the other is categorical nominal. So you can use the information gain or entropy concept to find a relationship between them. So another measure, which is not very common but very simple to compute for such pairs of attributes, is called AUC. AUC is actually used in machine learning in other contexts as well, but it can also be used to determine the relationship or the strength of the relationship between a categorical attribute and a numerical or ordinal attribute. So AUC actually stands for area under the ROC curve, ROC curve, or receiver operating characteristic curve. So this is often used in machine learning to evaluate the performance of machine learning algorithms. But here you can compute AUC directly on the data set, and it will give you an idea of the relationship between them. AUC, of course, varies between 0 and 1. And here 0.5 means no relation or close to independence. And a value of 0, either 0, 0 is relationship in one direction, 1 is relationship in another direction. Both of these means the strong relationship. तो just to take the very simple example, gender का example ले लेते हैं. So let's say आपके पास data set है gender का, male and female का, income का, and you sort the data according to income. So let me write the sorted values. So let me use one extreme first. So let's say female, 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 male, male, male. So this is sorted. So female, the first female, yeah, all three females have income less than. So let's say मैं incomes भी लिख लूँ आगे, जो 10 का है 10K, so 12K, 15K, फिर males शुरू हो गए, let's say 20K, 25K, and let's say 30K. So using the income, you are sorting the gender. All right. And then just looking at the sorted values of gender, you can compute the AUC. So how you take one value, of course, how many values do we have? And total values is 6, right? So you start with the sorted list of gender, and let's say I will count the number of course, this is only AUC, the simplest form only works when the categorical attribute has two values. So binary values. If you have more than two values, then AUC would not work. So that's one other, you can say, characteristic of AUC. While information gain can be computed for, or entropy can be computed when the categorical attribute has more than two values. So this only works for binary values. Of course, there's an extension to this for other values that's more complicated. We won't discuss that. So what I was saying is, how do you compute it? So you fix one value as the one that you count. So let's say we count for all the Fs. So you look at the first F in the sequence and count the number of M's that occur before it. So 3 M's occur before it. So look at the next F. How many M's occur before this F? 3 again. Look at this F. How many M's occur before this? 3 M's again. So then the AUC is simply computed as, for each F, count the number of M's that occur before it. So 3, 3 plus 3. So there are 3 F's and each of them, 3 M's occur before them, divided by how many M's and F's there are. So there are 3 M's and there are 3 F's. Their product, of course. So you get a value of 1. So AUC is 1, which means that there is a strong relationship between income and gender, as you can see from. So if someone tells me the income, let's say someone tells me an income of 11K, I know for sure that is going to be a female. If someone tells me an income of 25K, I know for sure that is likely going to be a male. So using this simple approach, you can find the relationship between a binary attribute and any ordinal or numeric attribute. So let me just quickly take another example, because I'm just explaining this more because you won't find this in most textbooks. chi-square वगैरह तो आपको मिल जाएगा. So let's say मेरे पास कोई एक और order आता है of males and females. So let's say मेरे पास पहला female है, फिर male है, फिर let's say फिर male है, फिर female है, and then let's say, let me just do 6 again. ये 4 हो गया. So एक और F कर लेते हैं, ठीक है. So how many F do we have? F
3F
M?
and 2M.
Okay, ठीक है. So total मेरे पास हो गया 5. 5 भी कर सकते हैं, no problem. ठीक है. All right. So let's again do the same analysis and take each female and count the number of males that occur before them. So if you look at the first, so first F, उसके पीछे कोई मेल नहीं है. Of course this is ordered है, ठीक है ना. तो 0 हो गया ये, ठीक है. प्लस दूसरा M है, M नहीं लेंगे हम. दूसरा M है, ये भी नहीं लेंगे. फिर 2 F है, दोनों F के पीछे 2 M's हैं. तो हमारे पास फिर you have 2 + 2, ठीक है. 2 F's के पीछे 2 मेल्स हैं. अब टोटल हमारे पास 2 मेल्स हैं और 3 फीमेल्स हैं. So 0.6, 0.66. So this is, as you can see, the males and females are more or less jumbled up. Of course, this is a very small data set. So they're jumbled up, so you get a value close to 0.5. So any value close to 0.5 means that you don't have a strong relationship between gender and income. Of course, you can flip this. In this case, we computed, you took female as the anchor and computed males that occur before it. You can do the inverse as well. So let's say if I take males and count the number of females that occur before them. So इसमें मेरे पास 2 males हैं. पहली male का पीछे female 1 है, दूसरे male का भी नीचे पीछे female 1 है, ठीक है. Divided by, of course, 2 × 3. So you get a complementary value on the other side, 0.33. So this just, I mean, it's still saying that it's not a strong relationship. So it's close to 5, it's not close to 0 or 1. Or in a way, it's kind of in the middle, but still it's indicating that it's not a strong relationship.
Excuse sir?
Yeah, question?
Yes, sir. सर लास्ट एग्जांपल में 3 + 3 + 3 लिखा है, लेकिन फीमेल
Just
के
hold on, let me
पीछे
increase
जो
the volume. आवाज नहीं आ रही आपकी.
ओके
हाँ जी, आप बताएं.
सर, कैन यू हियर मी?
जी, आप बेहतर.
सर लास्ट एग्जांपल में आपने लिखा है 3 + 3 + 3, तो फीमेल के पीछे तो कोई भी मेल नहीं है, तो हमने फिर ये क्यों लिखा 3? लाइक स्टार्ट ही एफ से हो रहा है.
हाँ जी, तो वी आर टेकिंग start F से हो रहा है, taking male. Okay, so we have taken male as the anchor. If you take female as the anchor, तो फिर ये हो जाएगा 0 + 0 plus 0 divided by 9, which is of course 0. मतलब
Okay.
उसका complement दूसरी side पे आ जाएगा. It still shows that there is strong relationship.
Strong image. Okay, sir. I understand.
ठीक है, तो वो हमने एंकर दूसरा ले लें तो उल्टी तरफ आ जाएगी वैल्यू.
Sir, how finding this relationship is helpful in data integration?
They
can
tell
understand the
you, they
link.
give you an indication of how two attributes might be related, and then it's up to the data miner to decide whether this is because of redundancy or whether it's some other relationship. So we are just discussing some measures to filter out potential issues of redundancy. So in this example that I gave of gender and income, obviously there is no redundancy. ठीक है ना? तो इसमें redundancy का issue नहीं है. But in other scenarios, there might be issues of redundancy. So for example, let's say, hypothetically, let's say gender ही है आपके पास एक साइड पे, और दूसरी साइड पे ना आपका कहीं और से आपने डेटा सेट लिया है, उसमें भी जेंडर ही था. एक में एम लिखा हुआ था, दूसरे में कोडिंग हुई हुई थी 1 और 0 की. And you don't really know whether that 1 or 0 is a numeric attribute or a integer attribute or so on. So you can then do a correlation analysis and find out whether they are strongly related or not. If they're strongly related, then you might dig into deeper, and maybe you later find out that they're actually the same thing. In one database, you encode them with M and F, the other you encode them in 1 and 0.
Okay.
ठीक है, ऑफ कोर्स इस केस में ना दोनों ये कैटेगोरिकल है, बट सिंस एक में वैल्यूज यूज हो रही थी तो यू आर नॉट श्योर के वो कैटेगोरिकल है कि नहीं है. इट माइट बी न्यूमेरिक एंड सो ऑन. So you then applying some of these techniques to quantify the relationship. And if they're actually exactly the same, then उसमें तो आपको strong 1 or 0 answer आएगा.
So if we have 1 or 0, we can combine that attribute, right?
Yes,
हम इसको
you can
integrate
only
कर
keep
सकते
one
हैं.
of them. मतलब
Okay.
redundancy है ना, तो आपको पता है दोनों same है, तो आप you can just keep one and not both.
Okay.
ठीक है, तो all right. So we talked about some measures. One other category of measures, which again, I wouldn't go into too much detail, but let's say we have ordinal and ordinal. Ordinal मतलब rankings हैं आपके पास. Let's say एक आप grade है, ठीक है, और दूसरा भी let's say rankings ही ratings नजर आ रही हैं आपको किसी की, ठीक है. Both of them, but they are using symbols for grades and for ratings. So you can, for this case also, you can use information gain, or you can even use chi-square, you can even use entropy. AUC of course यहाँ नहीं होगा, because AUC जैसे मैंने कहा एक attribute जो है वो binary होना चाहिए. But for ordinal or ranking based attributes, there are some other measures out there, which of course I won't go into detail, but आपको पता होना चाहिए. One is called Pearson coefficient, which is very similar to the Pearson correlation coefficient for numeric attributes. This is based on rank. That was based on mean. So this is based on rank. Pearson correlation coefficient. इसी तरह एक दो और भी हैं, Kendall coefficient. So all of these measures are based on ranking. So if you are, so basically if you rank one attribute, how does the rank of the other attribute relate to the ranking of the first attribute. If there's a strong relationship, either let's say one is ascending, the other is descending, and so on, then you'll get a very you can get a strong value for these measures. Otherwise, you'll get a independent kind of value from these measures. ठीक है? All right. So all of these measures that I mentioned were mentioned in the context of data integration. And for data integration, the whole issue was to determine duplicate or redundant attributes. But all of these measures are also useful for understanding data as well. So they could also be used for data understanding. जैसे मैंने income और gender की बात की, तो if you wanted to get a better understanding of income and gender, तो आपको ये entropy या AUC निकाल के वो एक understanding gain कर सकते हैं. ठीक है? So they are not explicitly important for integration or redundancy detection. They have other purposes as well. So it's just that we are discussing this in this particular category, but they are also important in other categories as well. All right, so any questions? Let's try to move on. Any questions? So do you want me to discuss the calculations of chi-square or covariance and stuff like that? I think you can always look into the slides and get them. So basically for computing chi-square, you need to create the contingency table. So contingency table basically is for each value of one attribute, and for each pair of one attribute value, another attribute, how many times that value occurs. That is observed value, and then you compute an expected value. Expected value is इधर अब जो numbers हैं मुझे let's see numbers क्या है इधर. So they are so you have play chess and like science fiction. So reading habits and sports habits, right? So they are two attributes. एक में दो values हैं, which is play chess and not play chess. So two possible values for whether a person likes chess or not. And the other, of course, is reading habits, likes science fiction and does not like science fiction. Of course, ये multiple values भी हो सकती हैं. So science fiction, for example, fantasy, adventure, and so on, multiple भी हो सकता है. So you get a contingency table, 2 by 2 table. ठीक है? So 250 क्या चीज है? This is the observed values in our data set. In other words, there are 250 students or people who play chess and like science fiction. 90 जो है expected value, वो भी मैं बताता हूँ बाद में किस तरह निकलती है. So यहाँ 200 है. So people in our data set who play so do not play chess and like, for example, fiction is 200 and so on. So इस तरह आपका ये सारा टेबल भर जाएगा. So हर कॉलम का आपके पास एक सम भी आ जाएगा. So 450 450 1050 and total sum of all the examples is 1500. So in other words, in our data set there are 1500 students or people for which we have recorded these values. So 1200 for not playing chess, 300 for those who play chess. ठीक है? So expected value किस तरह निकालते हैं? ये 90 किस तरह निकला है? So 90 basically this 450 multiplied by this 300, right, divided by 1500. So 450 multiplied, meaning the उस सेल का जो रो का सम है और कॉलम सम है उसको मल्टीप्लाई करें divided by 150. This basically is assuming that these two values are independent. एक की total value ली, दूसरे की total के साथ cross multiply किया and divide by the total. So independence से जो expected value निकल रही है वो independence से निकल रही है, observed है, दोनों के difference का square करके सारों का sum कर देते हैं. This will give you the chi-square statistics. So for example, if I want to compute this, $450, so 300. So for example, if I do this, 450 into 300 divided by 1,500. So what do you get? 90. 90, right? So this is expected value, assuming that both attribute values are independent, both attributes are independent. So अब उसमें हर सेल को आपने फिर कंप्यूट करना है 250 minus 90 whole square divided by 90, the expected value, and you sum for all cells.
So what is this 90 representing?
This 90 is representing that if both of these two attributes were independent, then you will have 90 people who play chess and like science fiction.
Okay. Okay.
So, and of course, in the chi-square computation, so you notice in the numerator, we are subtracting the observed value with the expected value. Expected value is based on independence. So जितनी ये बड़ी वैल्यू होगी, इसका मतलब है कि deviation from independence जा रही है, मतलब dependence की तरफ जा रहे हैं हम. So that's why the chi-square value, which is larger, means that they are dependent. Chi-square values that are close to zero is independent. Of course, if you go into details of stats of this, so degree of freedom भी आप निकाल सकते हैं. Degree of freedom निकालने के बाद आपके पास एक नंबर आ जाएगा कट ऑफ. उस कट ऑफ के बेसिस पे आप फिर बता सकते हैं विद सम परसेंटेज ऑफ कॉन्फिडेंस के ये आप इसको इंडिपेंडेंट कहेंगे या डिपेंडेंट कहेंगे. तो वो चीज़ें वी वोंट गो इनटू द डिटेल. As a data miner, you need to eyeball these numbers and make a quick decision. ठीक है, बहुत बड़ी वैल्यू आ रही है तो इसका you know that there's a lot of relationship between those two attributes. ठीक है, so that was the chi-square. और एंट्रोपी हम एक्चुअली बाद में भी अब देखेंगे, मे बी अभी आई विल ट्राई टू स्किप इट. एंट्रोपी कंप्यूटेशन, मोस्ट ऑफ यू माइट हैव स्टडीड एंट्रोपी एल्सवेयर एज वेल. सो लेट्स मूव फॉरवर्ड. सिमिलरली कोरिलेशन भी आपको पता ही है, बट यू कैन लुक एट दिस स्लाइड्स एंड गेट द आइडिया. कोरिलेशन एंड कोवेरियंस. And as I said before, if you can make a scatter plot and get an idea of the correlation. And this is of course only possible for numeric attributes. So let's move on to data reduction. So data reduction, as the name suggests, in this category, we have techniques that are meant to reduce the size of the data. And the reduction can be in multiple ways. And if you are considering a tabular representation of data, so reduction can be reduction in the number of attributes or features, or it could be in the reduction in the number of observations or examples or objects. So both of those cases would fall under data reduction. The whole idea of obtaining a reduced representation, why do you want to reduce the representation? Usually to speed up our analysis. If the data set is very large, then data reduction would help us get results quickly. But we would like our reduction technique to maintain whatever is of interest to us within the data. So remember, data reduction is also transformation. So many of these pre-processing techniques result in transformation or cause transformation in the data. So we need to be careful that if we are doing data reduction and transforming the data, we are not transforming it in a way that makes the data or changes the patterns in the data that we are interested in. Okay. So again, it's again a judgment call that you will have to make here. So the result should be the same on the reduced data set. So that's the goal. But of course, you cannot guarantee that 100% in all scenarios. So there's always going to be a trade-off. So within data reduction, you can have further classification or categorizations. One very popular categorization, dimensionality reduction. So feature subset selection is also another category which is part of the dimensionality reduction. And then we have what is known as numerosity reduction, which is more about reducing the number of observations or objects in a data set, while dimensionality reduction is about reducing the number of features in the data set. Okay, so let's look at some of these very briefly. So we have about 10 minutes. So we are talking about dimensionality reduction. Okay. So of course, dimensions are, you can say, the number of features. These are dimensions, and if we call them, there are m dimensions in our data set. So m is the dimensions in the data set. So why would we want to reduce the number of dimensions? Usually the issue of curse of dimensionality also arises because of many dimensions. So if you have many dimensions, then you need exponentially more data to get qualitatively similar results. So that essentially is curse of dimensionality. So if you remove dimensions, maybe qualitatively you will get better results even if you have smaller data set. And of course, we would like to reduce the dimensions such that the dimensions or features that are most value to us are retained, and the features or attributes that have least value to us are removed. Okay. So usually in dimensionality reduction, so basically dimensionality reduction may typically we are not selecting from the set of attributes, we are actually transforming the set of attributes and then selecting from those transformed set of attributes. So original attributes जो भी थे आपके, let's say m attributes थे आपके, so you first transform them into some m again the same number, so m original attributes, and then you have m transformed attributes. But the transformation is done in such a way that you have a clear picture of which attribute is important and which is not. So maybe there's an order in them. For example, now you have order, let's say m, let's say मैं कहता हूँ 3 है, and let's say those attributes are A, B, and C. So after you have transformed them, you might get attributes A prime, B prime, and C prime, and the order that you have found based on importance is C prime, let's say A prime, and B prime. Okay. So if you want to now work with only one attribute, let's say, or one feature, you will just use C prime. If you want two features, then you use C prime and B prime. A था क्या था दूसरा? A था शायद A prime. And if you want all three, of course, you'll be using all three, which is of course pointless. There's no dimensionality reduction. ठीक है? So डायमेंशनलिटी रिडक्शन टेक्निक्स में ट्रांसफॉर्मेशन होती है, जो ओरिजिनल एट्रीब्यूट्स है वो ट्रांसफॉर्म हो जाते हैं इनटू सम न्यू स्पेस, एंड दोज attributes would have of course some new meanings. That's why I call them A prime, B prime, C prime. So that's one thing. The second thing is usually that technique is based on some criteria on which you can rank these attributes. And let's say the ranking is C prime is most important, A prime is next, and B prime is the least important. Now it's up to you. Okay, you can, if you wanted to work with just one attribute or one dimension, you just use C prime. If you wanted two, then you use C prime and A prime. ठीक है? So इसमें जो most popular technique है is of course called PCA. There are other techniques as well. So principal component analysis है. So this technique basically creates new attributes or new features, and it ranks them based on the variance of the observed data along those features. So what does this mean? So usually it's drawn through a pictorial fashion. So let me see. देखते हैं इसको यूज कर लेते हैं. Just a second. All right. So basically, so let's say you have a data set, original data set, and I'm drawing data cloud. Let's say ये आपका data cloud है, meaning that there's a lot of variance along this axis, right? So if you wanted to keep just one attribute, of course this is a 2D data set, एक y-axis भी है इसका, एक x-axis भी है, ठीक है? But if you wanted to keep just one attribute, you will probably keep the horizontal attribute because उसमें सबसे ज़्यादा information है, because उसमें सबसे ज़्यादा variance है, ठीक है? So the other attribute में variance बहुत थोड़ी है, कितनी variance है? Maybe इतनी थोड़ी सी variance है, maybe उस सारी variance को एक ही value से represent कर सकते हैं आप, rather than keeping all the values just represented with one value. So this is the idea of PCA. So PCA finds such axis along which you have maximum variance, along which you have minimum variance. So let's say आपका क्लाउड यूं है, आपका क्लाउड लेट्स से यूं है, टेढ़ा क्लाउड है. अब नाउ यू नो द वेरिएंस, अब इस along this डायरेक्शन सबसे ज्यादा है और उस डायरेक्शन सबसे थोड़ी है. सो लेट्स से ओरिजिनल मेरे एक्सिस ये थे, ठीक है? What would PCA do is it will define axes like these. और ये जो नए एक्सिस हैं, this would be my x prime and my y prime. ओरिजिनल मेरे पास x था और y था. अब मैं इस डेटा सेट को आई जस्ट रिप्रेजेंटेड विद x prime if I wanted to keep just one feature or one dimension. y prime को मैं ड्रॉप कर दूंगा because x prime के along variance सबसे ज्यादा है, ठीक है? And of course PCA does this using by solving some eigenvalue eigenvector problem. उसकी डिटेल में हम नहीं जाएंगे. You probably be using some tool, Python में coded होगा. Let's say if you're using MATLAB या R, उसमें भी available होता है PCA, ठीक है? So essentially आपको PCA एक weighing matrix दे देगा W. So let's say आपके पास डेटा है, ओरिजिनल डेटा है X of size n number of observations into m number of dimensions. ठीक है? So आपके पास weighing matrix आ जाएगा after PCA. Originally this would be of dimension m by m, but these m dimensions would be ordered. So based on that ordering, you define, let's say आपने सिर्फ k features maintain करने हैं, तो you drop some columns m into k where k is less than m. कुछ columns आपने drop कर दिए at the end, ordered होगा. पहला column is the most important, second is the second most important, so on and so forth. So let's say if you're done this, आपके पास जो नया x होगा, prime कह लेता मैं, apostrophe would simply be x into w asterisk. This is of course a matrix multiplication. ठीक है? X is of size n by m, w is size by m by k. So what would be the size of x asterisk? So this would be m into k. So now you have a data set which is of reduced size. Dimensions are k, but these dimensions are based on the notion of variance, and they are the most, so these values are based on the top k axis along which there's highest variance. So now you can do most of your future analysis on this new data set, X star. ठीक है? Okay, we are out of time actually.
Sir, I have a question.
जी.
How the weighing matrix is m by m?
The weighing
The
matrix
W?
m by m.
Yes, you wrote w as m by m.
जी.
How is that and not n by m?
It depends on which technique you're using. So there might be a slight SVD use कर रहे हैं, उसमें कुछ और होगा. But here of course जैसे मैंने इसको multiply किया x से, so x से multiply करेंगे तो you are multiplying the dimension m with the dimension m. If it was n by m, वो multiply ही नहीं होगा. तो usually जो weighing matrix होते हैं वो original जो निकलता है it's a square matrix based on the number of dimensions that you have. And if you want to reduce the number of dimensions, तो जो उस matrix के जो end वाले columns हैं पूरे वो आप उड़ा देते हैं and just retain the top k columns. So then you get m by k. So if you do that and then multiply x with the weighing matrix, you get a new data matrix which is of k dimension.
Okay, sure. Yes. Thank you.
Exact details जो है वो of course थोड़ी सी आप जब PCA की details में जाते हैं तो उसमें दो तीन और चीजें भी होती हैं. I didn't want to go into all of that. Of course आप किसी implementation में देखेंगे, उसकी help देखेंगे तो आपको समझ आ जाएगी. So basically this W is the matrix of eigenvectors. So pehla column is the first eigenvector, second column is the second eigenvector, and so on. All right, so let's end this session. Let me see. एक मेरा वो Zoom बंद हुआ हुआ है. Okay. So